Lesson 2, we're talking about slope fields and being able to connect those to differential equations. Here's an example of a slope field. Of course, we just saw that in lesson 1 also, but I can kind of see, I can see how the slope is going, and it's telling us what our parent function is going to look like, purpose of a slope field. But that's a family because it just depends on what your initial condition is as to where you're actually going to be drawing your slope. I think you can see that. So on our first example, we just have an x value, not a y value. We usually just draw little tick marks at only the points that are given, so we don't need to go crazy and do -3 and -4. So we will go ahead and pick the value where x is -2, maybe where x is -1, 0, 1, and 2. So if I take this -2 and plug it into our differential equation, that will give us the slope at that point where x is -2. So plug that in, we'll have a -8. So if I'll go over to our slope field here, where x is -2, I want to plot a -8 slope. That's going to be pretty steep going down. They should all be consistent, kind of, sort of. Plugging in -1, that will give us a -5. So again, it's going downhill, but maybe not quite so steep. And then at 0, plugging 0 in, we'll have a -2. So again, going downhill, but not quite that steep. And then at 1, our slope is 1. Now that's going to be positive. So I'm going to go uphill at about a 45-degree angle. And then when x is 2, that'll have a slope of 4. So a little bit steeper yet. Now I want you to look at this. I want you to think about what this function would be. If we were to do our separation of variables here, so dy equals 3x minus 2 dx, and take the integral of both sides, we'll have y equals, what would that be, 3/2 x squared minus 2x plus c. This is a quadratic, and we know that a quadratic is a parabola. Doesn't that look like a parabolic? Doesn't that look like a parabola going on there? I think you're starting to see the relationship between them. On example 2, now this one has both an x and a y. I'm going to tell you the first thing that I prefer to do, though, is to solve this so it's dy dx equals. We'll subtract that 2 over, divide by -y. So we'll have 2x over y. That's a differential equation that I want to be using. We really need to pick all points. I'm going to just kind of pick a few, like if we do -2 and 2. If we plug that in, we'll have -4 over 2, which is a -2. So at that point, we will have a slope of -2. Then what if we had -2 and then +1? So that would be a -4. So we're going to be even steeper still. I think you can see if we had -2 and then y is 0. Ooh. Notice that that means we'd have 0 on the bottom. You can't do that. You can't have 0 on the bottom. So that's does not exist. And do not put a vertical line there. If you put a vertical line there, you will have that counted wrong. So anytime you have a slope that is not defined, that does not exist, just leave it blank. What if we try -2 and then -1? So that would be a -4 over -1 is a +4. So that's going to be pretty steep going uphill. +4. And then if we try -2 and -2, that's going to be a +2. So not quite as steep going uphill. After a while, you'll see there's kind of a pattern to it. So I'm going to try next. How about if we just randomly pick 1 and then 2? So 1 and 2 would be 2 over 2, which is 1. So at the point 1, 2, I'm going to have a 45-degree angle. Let me make that one maybe not quite so steep, a little bit flatter there. If we try the point 1, 1, that would give us a slope of 2, so just a little bit steeper. And then how about the point, I don't think I want to do 1, 0, because I know that that one's not going to exist. So how about 1, -1? So that would be 2 over -1. That would be a -2. So going downhill, kind of a little bit of a steep slope. All right, I'm going to stop the video and I'm going to finish up my slope field. You do the same thing. All right, did my best to get my tick marks going, okay? And there's kind of a pattern to it. You will definitely see those. All right, let's flip over. Let's talk about reasoning with slope fields and really just trying to understand what's going on. So we want to compute the slope at these different points. So at 1, 1, we'll have -1. We'll have +1, looks like a -1, and then a +1. So dy dx is going to be positive in, looks like, in quadrant 2 and in quadrant 4. And we're going to be negative in quadrant 1 and quadrant 3. Now, these aren't always true. This is of this particular slope field, all right? So we're just looking at one example. So now we want to compute using our original differential equation. So how about the point 1, 0? Ooh, that's not going to work because you can't have 0 on the bottom. So D and E, ooh, it looks like all of these are going to be D and E because I have 0 for Y. So all of those are not going to exist. So write an equation that would describe the slope is undefined. Remember, a slope undefined is going to be vertical. So that's going to be an up and down. So that would be like x equals a, or it could be any vertical line. And then if you have a slope of 0, that's horizontal. So that would be a y equals, I'll call it y equals b, or it could be any horizontal line. So now we're going to compute these particular values. Maybe put my differential equation one more time here. So it's negative x over y. So that we have a -1, we'll have -1, we'll have a -1. It looks like we'll have a -1, all right? So what equation would express dy dx equals -1? And that would be y equals -x. Think about if we were to do a separation of variables on this, and if we were to take the antiderivative of each side, that'd be y equals -x. So if it's dy dx equals a +1, that would be y equals x. So y equals x is a diagonal line, 45-degree angle, going through the first and the third quadrant, whereas if y equals -x, that would be going through the second and the fourth quadrant. All right, using a grid, we're going to sketch a slope field, and then we're going to draw a particular solution. We'll write the equation. So I'm going to go ahead and stop the video and put down my slope field, and you do the same thing. Not my best slope field, but I got it done. So I did go through every single point, and I put it into our differential equation, dy dx equals -x over y. Now we want to do a particular solution through the point 0, 2. So 0, 2 right here. And I think I can see the curve. See how it's kind of going down, and then we have an undefined part, and it's going down, and then we have an undefined part. So kind of going maybe like that, something like that. Now I'm going to stop because it's undefined there. I think you'll see why in just a second. Now, what is the equation for this solution curve? Can you see it looks like a circle? Can you see that? So let's take our dy dx is equal to -x over y. Let's do our separation of variables. So y dy equals -x dx. Do the integral to both sides. 1/2 y squared equals a -1/2 x squared plus c. Now we have our initial condition of 0, 2, so we can definitely plug that in. So 1/2 times 2 squared equals a -1/2 times 0 plus c. So our c value is going to be equal to 2. So I want to plug that in. 1/2 y squared equals a -1/2 x squared plus 2. Let's multiply everything through by 2. So y squared equals a -x squared plus 4. Okay, now we got a couple things that we can do here. One is, let's just solve it for y. So we want to do the square root of both sides. So we'll end up with the plus or minus square root of a -x squared plus 4. However, Because our particular solution is above the graph, because it's above the x-axis, because it's a 0, 2, we do not want to have the negative value. It's going to be positive square root only. All right, so that would be our particular solution. Now, something else that I want to do, let me put this one in black here, is I want to move this negative x squared over. So we'll have x squared plus y squared equals 4. That equation, I'm hoping, is familiar to you. That's the equation of a circle, and with a radius of 2. And isn't that exactly what this looks like? It's just that we had to stop because our particular solution was only positive. All right, let's go ahead and flip over next. So I'm not going to worry about part G and part H. You can go ahead and look up the completed notes, and as you move left to right, again, this is for a particular example, so I don't think that's worth our time to look at that. But I do think this next part is definitely worth our time. We're going to be doing matching, and this is pretty common, that if you're given an equation and you're given graphs and you're supposed to be able to say, okay, which one goes with which? All right, so the first thing that I look for are anytime you have limitations. I'm looking at those graphs and you can see there's some slope fields that are just like starting at different points. Check it out. We have a square root function. Well, you know that the domain of a square root, you take whatever's on the inside, that has to be greater than or equal to 0, or x has to be greater than or equal to a negative 2. I think we see that one is D for sure. So D is the same thing as number 1. That was an easy one. Okay, any other limitations? Oh, natural log. Remember, you can't do the natural log of anything less than 1. And so y is required to be greater than or equal to 1 whenever you do natural log. And so this looks like we have this example E. So number 5 is going to be example E. So we've got 2 of them taken care of. Next thing that I like to look at is whenever you have ones that have only one variable. So if you have x, that means your x values are going to change, but not the y values. So as I move left to right on example A, my values are changing. But as I move up and down, you see there are no values changing because there's no y. So is there any other that are that way? As I move left to right, okay, on example C, as I move left to right, my y values are changing, but not the x values. Looks like on F, both x and y are changing, same with G. And H is just kind of, yeah, both are changing. H is definitely kind of a unique curve there that I recognize. So on example, so for 2, I'm going to say that one is A because it's the only one that has where the x value changes but not the y. Let's see. The other one that has only one, I'm going to skip 4 for just a second. Let's go to number 6. So that one has only y. So where do the y's change but not the x? We saw that on example C. So again, let's see. A was 2 and C was number 6. So we're narrowing down what we have. Okay, the cosine graph. This is one where only the x's are changing and not the y's. So as I'm going left to right, can you see, I guess we actually had 2 of these. We had A as well as H. Can you see that this kind of looks like a sine curve? Can you see that? So if you take the derivative of cosine, that's equal to a negative sine. Yep, negative sine. So H and number 4 go together. All right, now what we have left are ones that have both x's and y's. So let's just start plugging points. I want to do number 7 next. So what if we had the point, say 1, 0? I'm not really sure where 1 is at, so we're just going to have to kind of eyeball it. But if we have the point 1, 0, ooh, that would equal 0, right? Our slope would be 0. So where toward the right would our slope be equal to 0? It kind of looks like it's undefined on B. I'm not 100% sure. I'm thinking that that could be F. If we moved over to about 1, 0 to about right in here somewhere, that kind of looks like that could be it. 1, 0, I'm not really sure where it's, oh, I don't think that this is it because at 1, 0, our slope looks like it's at positive 1, so I'm pretty sure it's not G. So I'm thinking that number 7 could be maybe F. All right, let's go ahead and, okay, I'm pretty sure that it is not G, because if I scoot over, see how those are all positive, so I can eliminate that one. But I'm still trying to narrow it down between B and F. So let's try another one. What if we try the point, let's see, all of these are negative in the first quadrant. Not all of them are negative. So what if we try the point 1? There we go. Yeah, that won't work. I was going to do 1, -1, but you see how those are both positive. So how about if we try the point 0, 0? Let's just try 0, 0. So 0, 0 is going to give us 0. Oh, can you see that on F it looks like if you have 0, that's equal to 1? Yep, so that narrows it down. Number 7 matches up with B. Got to have a lot of patience with these. Okay, so we have 2 left, a sine and a cosine curve, and we're down to F, and we're down to G. Okay, I think I want to tackle the sine of y equals x. We know that sine of y is 0. Sine of 0 is 0. So maybe if we tried 0, 0, so that would give us a slope of 0. So where is 0, 0 equal to 0? Not at F, is it? Looks like that's going to be at 1. So I think that this one is G. And then let's go to cosine. If we try cosine of 0, 0, that would be the cosine of 0. Our slope would be 1. So at 0, 0, that little slope right there is 1. All right, so how in the world did we do all that? We kind of did a guess and check and kind of an analysis with it. So if we flip over toward the bottom here, what strategies did we end up using? All right, the first thing, that if your differential equation, dy dx, has only x, then the slope changes left to right and not up and down. If your differential equation, dy dx, has only y values, then your slope changes up and down. And of course, if your differential equation has both x and y, then your slope is going to change in both directions. Darn it. Those are the ones that are a little bit trickier, I think. So if your differential equation is less than 0, or if your differential equation is greater than 0, just think about which one matches. And we did that by plugging some points in. Another one is if your differential equation is equal to 0 or undefined, and that's actually where we started, like with our square root or the natural log. And then if we get really desperate, which we definitely got to, you can check ordered pairs. All right, one more example. Let's go back up to the top of this page to example 5. We are given the differential equation. Thank goodness we don't have to sketch that beast right there. And let's see, we want to use a slope field. We're going to sketch a particular solution, so through the point 0, 1. And then we're going to find a particular solution. So our point 0, 1 right here. So we're going to try to follow what that slope looks like it's doing. It looks like it's kind of flattening out a little bit. And then going down to here, it looks like it's kind of starting to get close to, looks like an asymptote there at -2. Which makes sense if you look at your differential equation. You have x plus 2, you can't have a -2 on the bottom. So it's going to start hugging that that vertical line, x equals -2. So this is our sketch of our particular solution. Now let's do our separation of variables. So I'm going to leave that x plus 2 on the right. I'm going to move the dx over there, so just have our dy left. We'll integrate both sides, so y equals the natural log of the absolute value of x plus 2. Right here, don't do anything else. Right here, right now, is whenever you plug in your initial condition or your particular point. 1 equals the natural log of 2. Oops, I made a huge mistake. After you take the antiderivative, don't forget your plus c, because the whole purpose of this is to solve for c. So our constant is 1 minus the natural log of 2. You'll take this and you'll plug it back in to that equation you got right after you took the antiderivative. So our particular solution, y equals the natural log of the absolute value of x plus 2 plus 1 minus the natural log of 2. And that takes care of lesson 7.2, dealing with slope fields.